Okay, we'll get started. So I'll talk about the midterm exam, and I wanted to do this cool application of the Metropolis algorithm, but then like on Piazza, I just saw a bunch of I don't know. Well, I want to clear up some misunderstandings, I think. So we'll take a little bit of time to do that. But let me talk about the midterm exam. Okay, so I think. I mean, I might make a couple changes, but I think this is pretty much, these are going to be the topics that we will test on. Okay, so one is you're going to do, what just happened? Hang on. Sure. And something happened. Okay, so we want week 6 Friday. All right, so first will be Bayesian, excuse me. I don't know. All right, well, we'll see. Okay. Bayesian Inference, or basically a model with a conjugate prior. Okay. And you have seen a couple examples. So examples we've done in class. Is the binomial or Bernoulli, slash Bernoulli model, Bernoulli distribution with a beta prior, right? And then in homework 4, there's a problem where you have an exponential distribution with a gamma prior. Okay. And on the exam, it probably won't be these ones, but the concept is going to be the same. All right. So the exam, probably not these same problems, but similar concept in that you got the data you come from a certain distribution, except the parameters that define that distribution are unknown to you. Okay, so so in the problem, you will get data that come from a distribution, except you do not know the parameter that defines the distribution. So for example, in our Bernoulli or binomial example with the beta prior, we said your data is coming from this bucket that we are drawing with replacement, right? So basically the data is coming from a Bernoulli distribution, or if you want to keep track of multiple observations, then a binomial distribution. Except the parameter that defines the bucket, the proportion being green, that parameter is unknown to us, okay? So, so you don't know the parameter that defines the distribution, okay? You are given a prior distribution for the parameter. You're given a prior distribution for the parameter, and then finally, so what you need to do is you will find basically a likelihood function for the data, okay, over of a parameter value. So it's, the likelihood of getting this data for different parameter values, and then, you'll multiply that by the prior to get something proportional to your posterior, which will allow you to find the posterior distribution, okay? Multiply the likelihood by the prior to get, something proportional to the posterior. Okay, and then ultimately you'll find the posterior distribution. Does this make sense? So if you understand basically the first homework problem and homework 4, then you'll have the kind of the setup for this, except that first homework's kind of like an exponential with gamma. Maybe it'll be that. Maybe it'll be something different. Okay, you can go on Wikipedia and see kind of different things with conjugate priors, but there's too many to memorize. Okay, but if you understand the concept, you can make up some practice problems for yourself with different things, and you multiply your observations together for your likelihood and things like that. Okay. Are there questions on this? All right. Let's. Okay. You'll get another problem where it'll be Metropolis Algorithm. For a discrete distribution. Okay, so this will be similar to the island hopping example. Okay, so I'll provide a discrete distribution. Basically a target discrete distribution, okay, and kind of maybe a description, and then basically you will use the Metropolis algorithm to figure out the complete transition matrix. Okay. So you'll figure out the transition matrix, which shows, the probabilities of moving from one state to another state, and the probability of remaining back on itself. Yeah, and then I don't know what else. Maybe do some multiplication with the transition matrix. Okay, so this is so there's a problem in homework 4 that talks about making the transition matrix for the island hopping example in the textbook. Okay, so you set that up yourself, and I've done an example at least for maybe 3 of the lines in the class notes, right? So we did it for, you know, island 1, island 8, and I think island 4. And then, you know, your homework is to figure out islands 2, 3, 5, and 6, which isn't that hard. Okay, and then be prepared to do it on the exam as well. Okay, so similar to island hopping example, you know, there's a we have seen basically transition probabilities for islands 0, 4, and 7 in class notes. Okay, and then in the homework, in homework 4, you have to figure out the rest. But you know, the test problem is not going to be exactly the same, right? So don't get mad at me that the test problems aren't exactly the same as the homework, okay? But just, I'm thinking this is similar, all right? All right, questions on this? We're good, okay. All right, and then, okay, and then we'll have a Metropolis algorithm. Metropolis algorithm for I guess a, you know, general infinite distribution. All right, and then, and so in this case, basically I will provide you some random numbers, like sampled from our uniform, and you'll have to decide, you know, where you're going to go based on that, and you know, what your acceptance ratio will be and whether you'll accept that value or not. Okay, so it's basically kind of like, I'm going to make you do maybe like 2 manual iterations of the Metropolis algorithm. Okay, so 2 manual iterations for Metropolis algorithm. Okay, and for each iteration, I will provide some random numbers. Okay, you use one random number, the first random number, to propose where to go, and then you'll use the second random number to decide to accept or reject the proposed value. Okay, and of course, you know, I will tell you what your target distribution is, I will also tell you the proposal distribution. And I'll try to keep the proposal distribution simple enough that you can easily go from a random uniform to a proposal number, if that makes sense. Well, I suppose I could even give you like a random normal table, couldn't I? And that would help. Well, that gives me an idea. All right. So I'll tell you a proposal distribution. Either it will either be simple enough, or I'll give you a random normal table. Okay. Simple proposal, or I provide a standard normal table. So you can go from our unif to basically the random proposed. Okay. Are there questions on this? Like if I gave you the random normal table, and not the random normal table, a standard normal table, like the your Z table from stats 10, you would be able to go from random uniform to random Z, right? Because basically you have the you have capital F or capital Z, whatever you call it. You have the CDF of the normal in the CDF normal table, right? And then you could just use inverse CDF method. So like if I gave you your random uniform is 0.5, you would tell me that your random Z is 0, right? And if I gave you random uniform is I don't know, 0.975, your random Z would be 1.96 type of thing. You're just going from it's inverse CDF method, right? Maybe that's, I don't know. We're okay.
Yeah.
Okay. So if I give you a standard normal table, you can do inverse CDF method for random normal, which would be similar to Metropolis Algorithm, right? And then once you have your random proposed value, then you figure out your probability of the proposed versus probability of current. You take the ratio between those two, and then you choose to accept or reject. Maybe. Okay. All right. Okay. Any questions? So this is pretty much what the midterm exam will look like. Of course, all right. All right. I wanted to address some misunderstandings that I was observing on Piazza. Before I get into, I had this, I don't know, what I thought was a cool demo, but I don't think we're going to have enough time for it today. So I guess we'll do it after the midterm, and just to clear up some misunderstandings. Okay. Okay, let me close our poll here. All right, let's see. Okay, credibility interval versus, well, all right, there's a lot I've got to talk about. Okay, first of all, let's talk about what is a likelihood function, okay? The likelihood function, okay. The likelihood function is a function, it's a function of the parameter. Okay, and in the likelihood function, we treat the data as fixed. Okay, we treat the data as fixed, and it's a function of the parameter. Okay, so I think we had something like, you know, the guy had 10 at-bats, and he had 4 hits, right? Okay. And then we wanted a function of the likelihood function of this data, right? So basically, the likelihood function is going to be the product. So we assume each data point is independent. Each observation is, we'll say IID, right? Is IID, okay? And so what that means is that the likelihood is just the product of each data point's probability. Okay, so in this case we had 4 hits, so this means it's going to be, if theta is the probability of a hit, then 1 minus theta is the probability of a miss. Okay, and so we have 10 at-bats, 4 hits. We're going to have theta times theta times theta times theta, and then we have 1 minus theta times 1 minus theta dot 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 times 1 minus theta, and this will boil down to theta to the 4th 1 minus theta to the 6th. Okay, so this is the likelihood of this data. So we have, you know, we would say something like, this is a function of theta, right? A function of theta, the probability of hitting the ball, is equal to theta to the 4th times 1 minus theta to the 6th. I saw someone label this the posterior. This is not the posterior. This is the likelihood. Okay, don't call this. This is the likelihood. This is the probability of our data given a value of theta. Yes, question. No, the likelihood function does not need to integrate to 1. Okay? The likelihood function, yeah, okay, so the likelihood does not need to integrate to 1. Okay, this is the likelihood if I treated all of these as independent Bernoulli things, okay? So we have a few options, right? We could have said we saw hit, 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 miss, 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 or whatever, okay? And that would be, we saw 10 realizations of independent Bernoulli trials. Or we could have said we had 1 realization of a binomial with n equal to 10, okay? And in that case, you might throw in a constant there in the beginning. But even then, your likelihood function is proportional. So it's still proportional to, you know, 10 choose 4 of theta to the 4, 1 minus theta to the 6. Okay, these are proportional to each other, so it doesn't really matter in this case, okay? That's our likelihood function. The prior distribution is some distribution, okay? Now, if we use a conjugate prior, then in this case it would be the beta distribution, okay? Some distribution. All right, so we used a conjugate prior, and I said this was going to be a beta. What did I say? 81, 219, is that right? Okay, and this came from the reading. I saw a lot of questions, and I think it was clear that people just didn't do the reading. So, yeah, at the beginning of the homework assignment, it says reading, and then it says you're supposed to read this chapter, and then like I had 2 web links that talked about this. Okay, so make sure you do your reading. All right, so we had the beta this, and this is equal to theta to the 81 minus 1, and 1 minus theta to the, I better just double check beta distribution. Yeah, 1 minus theta to the b minus 1, right? So to the 219 minus 1. Okay, so we have theta to the 80 times some constant, right? So I've got constant times theta to the 80 times 1 minus theta to the 218, okay? So that's the prior distribution. And then the posterior is proportional to the prior times the likelihood. Okay, so our likelihood times the prior. So the prior, we have a constant times theta to the 80 times 1 minus theta to the 218. And our likelihood is theta to the 4 times 1 minus theta to the 6. Okay, which means our posterior, so the prior distribution is probability of just theta. And this is the posterior probability of theta given the data is proportional to this. Okay. So in this case, we've got theta given the data is going to be proportional to, and I multiply these together, and I got theta to the 84 and 1 minus theta to the 224, right? And I want to get this in the form. Can we get it into the form of a beta distribution? And then we can write, this is going to be a constant times theta to the 85 minus 1 times 1 minus theta to the 225 minus 1. Sorry, that's running out of space here. All right, and so this becomes basically a beta of 85, 225. And by getting it into this form, we don't have to worry about the constant because the constant is taken care for us by using this thing. Is that okay?
We just call it a constant and then kind of ignore it, just bring it down, and then we don't have to worry about it.
Well, we know it's proportional to this, and we just know it's proportional, so it's this thing. The posterior distribution is exactly this thing multiplied by some number, and that number's only purpose is so that the thing integrates to 1.
Okay.
Okay? Is that all right? Okay. I guess we can take a look at homework 4 problem 1. So I said we had y comes from an exponential distribution, right? right? And the PDF of the exponential is lambda e to the negative lambda, I guess in this case it'll be lambda y. So we'll just pull that up. Exponential distribution. Okay, so our PDF is lambda e to the negative lambda times, in our case we're going to use y. And then we have the gamma distribution as our conjugate prior. Whoa, slow down there. Okay, and we're writing it in this form. The gamma distribution has two parameterizations. We're going to do it in this form, okay? So the gamma distribution, and then we say the conjugate prior is the gamma, which has the PDF basically beta to the alpha, what is it? Gamma of alpha times x to the alpha minus 1 e to the negative beta x. Okay, this is a constant. There's no x in here, okay? And then because we're dealing with lambdas instead of x's, I'm going to go ahead and just replace the x with lambda, and I think that'll help us see this a little bit better. Okay, so I've got lambda and lambda there. So we have our conjugate prior as a distribution of lambda. Okay, let's just say my prior for lambda is going to be gamma, and I'm going to just make stuff up. Gamma 5 comma 2 or something like that. Okay, let's say this is our gamma distribution. So therefore my PDF is going to be a constant times lambda to the 4 and e to the negative 2 lambda. Is that okay? This is my prior distribution. Prior distribution of lambda. Okay, if I said so homework problem 1, I'm going to just hear is similar to this. Okay. All right, and then let's say my data for y is 0.4, 1.2, and 0.4. Okay, we'll just keep it simple. All right. So these are the observations I get for y. Okay. All right, and then so what is my likelihood? Likelihood is equal to the product from n equals 1 to 3, because I've got 3 observations, of lambda e to the negative lambda y. So this is going to be lambda e to the negative lambda times 0.4 times lambda e to the negative lambda 1.2 times lambda e to the negative lambda times 0.4. Okay? And if I combine all of these, I would get lambda cubed and e, and I think I picked these to get e to the negative 2 lambda. Is that okay? All right, when we multiply all of these, we add our exponents together, and 0.4 plus 0.4 plus 1.2, yeah, okay. So anyway, so this is my likelihood function of the data. We're treating the data as fixed as a function of lambda, okay? And then so So what do I have is, so my prior was gamma 5,2, which is lambda to the 4 e to the negative 2 lambda. And then my likelihood we found to be lambda 3 e to the negative 2 lambda, right? I'm just going off of the memory of what I wrote, and I'm pretty sure this is right. Okay. And then, so the posterior is going to be the product of my likelihood and the prior, or something proportional to it. So this is going to give me lambda cubed e to the negative 2 lambda times lambda to the 4th e to the negative 2 lambda, and I would get lambda to the 7 e to the negative 4 lambda. Yeah? All right, and we want to get this in the form of a gamma distribution, which is in the form of a constant times lambda to the alpha minus 1 times e to the negative beta lambda, right? So what is alpha? Alpha is going to be 8. And what is beta? Beta is going to be 4. So this is in the distribution, we've got a gamma 8, 4 as our posterior. Okay, and that will take care of the constant in the front. It's good? Questions? Pretty much did homework problem 1 for you. Okay. Other misunderstandings I saw. Confidence interval versus credibility interval, and people were like, why does this thing look so different? Well, that was the whole point of the homework exercise, okay? So classical statistics confidence interval, right? So you have confidence interval from classical statistics. That's just p hat plus or minus z star times your standard error, right? And your standard error is equal to the square root of p hat times 1 minus p hat over n, okay? This can only take into account, the classical method only takes into account the data that you have. Right? So if you only have 10 data points, your confidence interval is going to be very wide, okay? And in fact, you're not even supposed to use the classical confidence interval because you're not meeting the large sample condition, but we'll pretend like it's okay. All right? So when you have a small data set, when your data set is small, your standard error is huge, which means your confidence interval is huge, okay? When we're talking about the credibility interval, there's no easy formula for it. This is basically a compromise between your prior beliefs and observed data. Okay? So if you've only seen a little bit of data, then you're going to count on your prior beliefs a lot more heavily, okay? So if you only have a tiny bit of data, okay, you will rely on your prior beliefs. And so, you know, if you had done the reading, okay, we would have talked about how in baseball, you know, the greatest hitter of all time had a batting average of like 36%, okay, and pretty much like the worst hitters that play a lot of baseball, are still over like 20% overall, okay, and so prior to seeing anything, we can be fairly confident that someone's batting average is going to be between 20 and 35%-ish, 20 and 36%. And so if we only see 10 data points, then our credibility interval will reflect our prior beliefs that someone's batting average is going to be between 20 and 36%, okay? And that's what you see. So when you created your credibility interval for where you've observed only 10 at-bats, your credibility interval is pretty much the same as basing it almost solely on the prior information, okay? Which is basically you're saying, well, seeing 10 at-bats doesn't really give me much information. I can just pretty much treat this like an average baseball player that I don't know much about, and we're going to assume that that the batting average is between 20 and 36%, something like that, okay? Which is a lot more of a narrow interval than what classical statistics gives you, right? Classical statistics, you see 10 at-bats and you get 4 hits, you're going to get some interval that goes from like 20 to 70% or something like that, okay? Or 10% to 70%, something very, very, very wide, okay? But we can take into our prior baseball knowledge and just say, it's almost going to be impossible for anybody to have a batting average of 70%, okay? According to classical statistics, that is theoretically possible within the range of confidence, okay? That, because of random sampling, you could have a true proportion of 70% and get a random sample of 10 where you only get 4 that are yeses. Theoretically, that's possible in classical statistics, but when we're talking about baseball, it's pretty much impossible for there to be a human baseball player that's going to have a 70% batting average, okay? And so, we would not consider that, and so our credibility interval is based on pretty much our prior information. As we gather more and more and more information, such as having 5,000 at-bats where 35% of them are hits and stuff like that, then our confidence interval using classical statistics will have a certain, a tight range because you've got a lot of data. And then your credibility interval will also have a very small, tight range that will look very similar to the classical statistics interval. And they'll be off a little bit because the credibility interval is a compromise between the prior and the data, but they're going to look a lot more similar. Okay, and so the point of those exercises, problems 5 and 6, was to show that there's a huge difference between your credibility interval and your classical confidence interval when you have little data, but as more and more data are collected, they get a little bit more closely aligned. Okay, and then maybe I should have done a different exercise where, if you had changed your prior beliefs and whatnot, how does that affect the resulting confidence interval or credibility interval? That's what we have. Okay. All right, we'll end here. Good luck as you guys study this weekend, and we will see you guys on Monday. I will send out a seating chart on Sunday with where to sit, so keep your eyes, check your email for that, and we'll see you guys on Monday for the exam. Good luck.